Hi, welcome to Brain Gauge channel. I am Mark Tomerdahl, and this talk is about reaction time and reaction time variability. Reaction time is an extremely easy concept. You receive a stimulus on your finger and you respond right away. Generally, the brain gauge delivers a stimulus to the first digit and you respond either on the computer mouse, or if you have a Brain Gauge Pro, you can respond on the Brain Gauge Pro. Reaction time variability, a little bit different, and as you take the reaction time test, you'll notice that you'll see numbers flash up on the screen, and those are your trial by trial scores. And basically you have 10 or 15, 20 trials, and what we're interested in for reaction time variability is how much did those scores vary. For example, you may score 200 milliseconds on the first test, and then 200 on the next, and 200 on the next. And in that case, your reaction time variability is 0 if you get the exact same score on all of them. However, if you score 200 on one, and 160 on another, and 240 on another, and it bounces around like that, then your reaction time variability may be around 40 milliseconds. So that's kind of high. So, and reaction time variability tells you very different things than reaction time, and I'll discuss that in a minute. But basically, let's talk a little bit about different types of hardware that other people use to measure reaction time with commodity or commercial grade utilities. So what we have here is a graph that shows differences in methods of collecting reaction time. And keep in mind, we did this test robotically. We collected a bunch of measures we did a reaction time test where we either flashed a visual stimulus to a photodiode and then it robotically exercises the stimulus, or we deliver a tactile stimulus like you would get on the brain gauge and then robotically press the appropriate button for the response. And the graph on the left that you see over here, this is a graph on the left, is a measure of latencies of the different methods. And so, and what we have here in this first one, this is the latency, or how long it takes for a reaction time test to be performed on a mobile device. So with a visual task. So we had a mobile device, it flashed a visual stimulus up, and the photodiode picked it up and then responded robotically on a computer mouse. You see that latency is a lot higher than the other three stimuli. It just means it's extremely slow. That's roughly 500 milliseconds, but even more importantly, the variability is very large. And you look here, that is the visual task with the computer mouse, and a little better than that, or a lot better than that, is the brain gauge with the computer mouse. And then over here, this bottom one that's nearly perfect with hardly any variability is the Brain Gauge Pro, where the robot responded on the Brain Gauge Pro itself. Now you may say, oh, these latencies can be subtracted out, but over here on the right-hand side of the graph, or the right-hand graph rather, is the raw data with the reaction with the latency subtracted out, so you can actually see the differences, and you can see that there's an extreme amount of variability introduced. Now, these variabilities that were introduced for these other methods range from 70 to 370 milliseconds, and when we see things go wrong neurologically, it's usually in the 20 to 30 millisecond range. So if you get up well over 20 milliseconds, then there's something wrong. But if you're using one of these commercial grade devices, which aren't designed for doing reaction time, they're not laboratory instruments, then you're going to get, kind of garbage in, kind of garbage out. Anyway, that's our pitch for the Brain Gauge Pro, which has a 1/3 of a millisecond accuracy. Now, besides hardware that's involved, visual and tactile reaction time tests, just to understand, Visual reaction time has a lot of redundancy, and that's what's sort of basically we're demonstrating here with these multiple pathways. You flash a stimulus in somebody's eye, and then they hit a computer mouse, and basically what happens? Well, if something, let's say something happened to this pathway, well, something happens to that pathway, you're going to be just as fast. Or something happens to 2 more pathways, still just as fast. Easiest way to conceptualize this is think about what your visual reaction time would be if you covered one eye. Lots of redundancy. You have no problem reacting quickly to one stimulus to one eye as you do with 2 eyes. Whereas somatosensory system is what we call a high fidelity system. It's extremely clean signal, goes to the somatosensory system, and you respond right away. So let's look at reaction time, just comparing different assessment tools. And this is for concussion. This is a group study where we collected a lot of data. I think on this case we had 200 concussed subjects, and we looked at the control average. So on the left you see results using the brain gauge, and what is reaction time, and what was reaction time post-concussion at day 1 through days 15 through 21. And you see that the brain gauge detected that people were above average on reaction time for the first 2 weeks, and then they basically got into normal range. With an online cognitive assessment tool that actually used baseline scores, and baseline scores are what people collect pre-season, and then look at the difference between the tests that they take pre-season versus the tests they take post-concussion. You see that there's not a lot of difference, and that difference is pretty much gone after 4 to 7 days. So the other thing that we didn't do, we did not collect baseline data. We just compared it to healthy controls and compared that. If you have the increased accuracy, you can actually do that. So let's take a look at reaction time variability. Reaction time variability is actually even more sensitive than reaction time. And when you compare, just this is both collected with the brain gauge, reaction time to reaction time variability, you'll notice that days post-concussion, there was no recovery until about 3 weeks post-concussion. Now this matches with many physiological studies, both in humans and animals, in terms of how long does it take to recover fully from a concussion. And reaction time variability is very sensitive to white matter integrity and also attention, so you can think about how is it affected by attention is, well, if you can't pay attention on the task, then your numbers are going to bounce around a lot. Like I mentioned, 160 to 200 to 240, your numbers will bounce around in those values quite a bit because you're really not focused and you're having trouble paying attention. So even though your reaction time might be overall average the same, your variability shows up. Now, if we compare the reaction time data that we collected from the brain gauge with other published methods for just concussion, since we have so much data on concussion, that's one way to do it. D prime is a sensitivity index that's used in signal detection theory, but just higher numbers are better. And what's reported in a meta-analysis, that means a whole bunch of papers. One paper looked at a whole bunch of papers, and the average of that was 0.58. And those were all using baselines. They're all comparing preseason, postseason, or post-concussion data. D prime for the brain gauge, concussed versus non-concussed, is 0.79, so a little bit better. And again, we didn't use baseline. And D prime for reaction time variability with brain gauge, concussed versus non-concussed, 1.4. So it's almost twice as good in terms of signal detection theory. Now, it's really kind of fun to review all the papers that have been done and read through them and see what types of papers have looked at reaction time and what influences reaction time. I'm not going to read them all. I'm just going to point out some of my favorite ones. Basically, I really like punishment as a negative reinforcement, which is an old study. This was done in 1965, full disclosure. I was 7 years old. So I had no part in it, but in that case, these people, the participants were shocked, kind of received an electric shock if they were too slow, and they found the results of that were that they got faster. You know, not quite as fun as taking caffeine or dark chocolate to get faster, but you know, those things do work. Reaction time variability has been shown in not quite as many papers, probably because people can't collect it. You have to use laboratory grade equipment to actually get decent measures. And sort of like the brain gauge, it's laboratory grade equipment. And, you know, lesions of the cortex, neurodegeneration, and as I mentioned, white matter integrity. Those are all things that lead to poor reaction time variability, as well as ADHD or lack of an attention. And in here I put a tuning curve because this was in another paper. Actually, I found this in a review from a very good review on a literature review on reaction time by Robert Kaczynski of Clemson University, who so kind of put his review online. But I just want to give an introduction to a tuning curve. And when you look at this graph, one thing that you'll notice is that there's an arrow right here, and that's optimal performance. So if you're measuring the reaction time, lower numbers are better, and the lower your reaction time, the better your speed score. And in this case, in this particular study, when arousal was extremely low, that's sort of like if you're sleepy, reaction time is poor. It's actually high. But reaction time is optimal in the middle of the day with a certain amount of arousal. But if you get really high anxiety and really high arousal, then your reaction time starts getting bad again. So tuning curves are generated for just about everything. So if you think that some supplement is really good for you, then, and maybe it is, but then you take too much supplement, you could actually make things worse because there's always an optimal amount for everything. Just because something in one quantity is good, larger quantity doesn't mean it's better. But anyway, it's something to think about, and think about tuning curves and think about numbers. It's very difficult to see what how good you are and what your perception of yourself is unless you actually measure. So I just want to give a quick case study, reaction time. And this is recovery from concussion. In this case, we're just looking at speed right here. This is this value right here. That is just the history of the reaction time. And again, higher numbers are better. So in this case, when the person was concussed, values are low, then they got better over time. Same thing for this case study. You see there's recovery from concussion. This took, from early October to late November. This person slowly progressed and got better. And not everything that we do has to do with concussion. So this was recovery from a migraine. Reaction time actually got better as this person recovered. And case study number 4 is from one of the subjects in TBI with pulse electromagnetic field treatment, where their reaction times were extremely poor at the beginning, but actually got very, very good over the course of a few months. So anyway, that kind of wraps up the reaction time talk. If you have any questions, feel free to email me directly to mark@corticalmetrics.com or go to the website for more info. Thanks for listening.